Hi, I'm Dr. Papia Bhattacharjee. In this problem, we have to find the volume of a solid region, and the solid region is already drawn. It's the region that's bounded by this plane that's given by 2x plus 3y plus 4z equals to 12 in the first octant. Okay, so it's the solid is bounded by the plane and the three other planes, the yz, xz, and xy. Okay, now let's recall first how do we compute volume using a double integral. It is the double integral over region R of the function f, that's a function of two variables, and then dA, which is dx dy or dy dx. Now, where is this region? This is the xy trace of the solid. So, wherever the solid is intersecting the xy plane. And where's the function? Well, the function is given by z. Now, look, our plane, the equation is given right here. So, we can rewrite it in terms of z equals, and then we will have our function right there. So, let's do that first. So, we have 2x plus 3y plus 4z is equal to 12. So, take the x and y term on the right hand side, which gives us 4z is 12 minus 2x minus 3y, and then z will be equal to 1/4 times that entire expression. And let's keep it this way instead of actually dividing each term by 4. Okay? So, our function f is right here. So, come back here and let's write that down. So, we have 1/4 times 12 minus 2x minus 3y dA. Okay. Now, let's try to understand this region R. Remember, it's the xy trace, right? So, if you look in this picture, where is the xy trace of this solid? Well, it's wherever it intersects the xy plane, which means it's right here. Now, let's try to understand that region in the two dimension so that we can figure out the bounds for x and y. Okay. Now, you see that there's a line and it's passing through 6 and 4, 6 on the x and 4 on the y. So, we can immediately graph it here, 1, 2, 3, 4, and here 2, 3, 4, 5, 6. So, the line is going to be right here. Now, we have to understand what line it is, right? What is the equation of that line? We'll get to that. But let's understand this region here is bounded by x-axis, y-axis, and the line. So, here's our line, here are the two axes. So, this is the region, the same region here. All right. Now, how do we figure out the equation of the line? Is the xy trace. So, we set z equals 0. So, we set z equals 0 in the equation, and you can actually consider the very top equation. If you plug in z equals 0, you will get 2x plus 3y is equal to 12. Let's solve for y. So, y is equal to, take the 2x on the other side, so 12 minus 2x and divide by 3. And that is this line. And this line is also the line here in the 3-dimension coordinate plane. Okay. Now, what do we have? We know that this is our region R, this R. So, we have to figure out the x and the y bounds. So, we consider our region and we draw our rectangle inside the region, right? And this is delta x. So, x is going to be my outer variable. And let's figure out where does x range? So x is between which values? Well, 0 on the left, and on the right, where does it cross? This is 6. And remember, the y is 4. So x is between 0 and 6. And what about the range of y? Look at the length of the rectangle. It's between x-axis and the line. So y ranges x-axis, that means y is 0, and the line is given by 12 minus 2x over 3. These are our bounds. Okay, so come back here and let's rewrite this double integral. Remember, the outer variable is x, so 0 to 6 goes to the outside integral, and inside one is y, that's 0 to 12 minus 2x over 3. And inside we have our function 1/4, 12 minus 2x minus 3y. And the dA, now we know x is the outer, y is the inner, so it will be dy dx. So that's the setup. And now we just have to solve this integral. Okay. So let's take out this 1/4 outside the double integral because it's a constant. It can be pulled out. And then we keep 0 to 6 as it is, and we just take this expression and try to find its antiderivative with respect to y. So x is constant, which means this entire 12 minus 2x is constant. Okay? So we will have 12 minus 2x, pull it out as a constant, and dy will give us y. Then minus, we have 3, and antiderivative of y is y square over 2. So this whole thing has to be evaluated between 0 and 12 minus 2x over 3 dx. Okay. Let's see. Plug in the upper limit for y, right? So we get 12 minus 2x times 12 minus 2x over 3, so we get a square and divided by 3. And next we have 3/2 times, again, y square, so this entire 12 minus 2x over 3 square. And then when you plug in 0, notice that both terms has y, so that will just give us 0, which is nothing. So this is our single integral. Okay, let's see. We have a 1/3, and here we can cancel out one of the 3's, right, because it's 3 square. So we will end up getting 12 minus 2x square over 3 minus 12 minus 2x square over 1, 3 gets cancelled, so 3 times 2 is 6, that dx. Okay. Now, simplify this a little bit. This is 1/3 minus 1/6. That's just 1/6. So you can pull out the 1/6, and then 0 to 6, we will just end up having 12 minus 2x square dx. Now it's pretty simple. So 1 over 24 here, and then you can just take the antiderivative. Remember, there's a chain rule involved here, and it is 12 minus 2x cubed over 3, and then you have to divide by -2 because that's the constant attached to x. So -2 as well, and from 0 to 6. Okay. So this ends up giving you, let's see, we have a 2, 3, we have a negative 1 over 24 times 6. And then when you plug in 6, notice, if you plug in 6, you get 12 minus 12, you get 0. So the first term is 0. Then when you plug in 0, you just get 12. So it's 12 cubed. Okay. And then finally, when you simplify this, you see you will get a positive sign, and then you will have 12 cubed over 24 times 6. Let's quickly compute that using a calculator. So 12 cubed divided by 24 times 6, and that's a 12. So the volume is 12 cubic units. That completes the problem. Thank you.